Let us see some application of uniform circular motion. A vehicle along a horizontal circular track. Here the bob is performing a horizontal circular track motion. We are going to find out the maximum velocity required for a vehicle to perform a horizontal circular track. Also, we are going to find out the minimum velocity required to perform a shunt in a well or wall of depth. This is also known as Motka Kuva. Third application is a vehicle on a bank road. Why the road is bank, we are going to see in this application. And fourth is conical pendulum. Here we are going to find out a periodic time of a conical pendulum. In this PowerPoint, we are going to see these two applications. First two applications. Let us calculate the maximum velocity of a vehicle along a horizontal circular track. So we consider a one vehicle, that is a four-wheeler car, taking a left turn on a horizontal circular track. There are three forces acting on this vehicle. First is normal weight, which is acting in a upward direction. Second is the weight of a body, that is always acting in a downward direction. And the third is force of friction, which exists between the road and the tire. We can consider a vertical section of this car like this. It is shown in this figure. This is a vehicle and this is a normal weight acting on it. Mg is its weight of a car, and the force of friction, it is always acting towards the center of a circular path. This force of friction prevents the vehicle from outward slipping or skidding, and this is a resultant force, which is a centripetal force acting towards the center of a circular track. This centripetal force causing a car to turn in a circular path due to the friction between the tire and the road. From the diagram, we can see that these vectors forces balances each other. The normal reaction, which is acting vertically upwards, balances its own mg, which is vertically downward. So we get the equation 1 as a n is equal to mg. Also the force of static friction between the road and the tire, it is always towards the acting towards the center, which is also equal to the centripetal force, or it balances the centrifugal force, and therefore we can write down the force of friction is equal to centrifugal force, and we can write the Fs is equal to m omega square r, where omega is a angular velocity, r is a radius of that circular tract. Then we can substitute the value of this omega, and we can get another equation of a that is a centripetal force as a mv square upon r, which is also equal to the static friction. Now let us divide the equation 2 by 1. By dividing equation 2 by 1, we get Fs upon n is equal to mv square upon r into 1 upon mg. Here m will get cancelled out, and we get the equation Fs upon n is equal to v square upon rg. This is the equation number 3. For a given track, we know that the radius r is always constant, and also for a given vehicle, mg is always equal to its normal reaction. And as the speed increases, the force of static friction Fs also increases. But this friction has a upper limit, and that is always given by Fs is equal to mu s into n, and where mu s is always equal to the coefficient of static friction between the road and the tire of a vehicle. Now if we substitute the value of this Fs in this equation 3, we can get the equation 3 as mu s n upon n is equal to V maximum square upon Rg. As the friction has an upper limit, this always impose the velocity also have some upper limit, and therefore we have written here V maximum square. Here also n will get cancelled out and we get the equation mu s is equal to V maximum square upon Rg, and ultimately we get the V maximum value is equal to square root of mu s Rg. This is the velocity for a vehicle moving along a horizontal track. Let us summarize all the equation to find the maximum possible speed of a vehicle which is moving along a horizontal circular track, which is equal to V maximum is equal to square root of mu s Rg. Let us find out the minimum velocity required for a vehicle to move in a well of death. So this is a well of death, that is a Maut ka Kuwa. We might have seen such kind of stunt in a circus or in some kind of mela. So what is this well of death? This is a vertical cylindrical wall of a radius r inside which a vehicle is driven in a horizontal circle. So this we always see while performing a stunt. Now let us find out a vertical section of this well of death. If you compare this to equation, so we find there are three forces acting in this wall of death. That is, first one is the normal reaction of this vehicle. As this vehicle is perpendicular to the wall of the death, so reaction is always acting towards the center of this circular path. The force of friction exists between the wall and the tire. It is always acting in upward direction. So direction of the force of friction is upward direction. Whereas the weight of this vehicle, it is always acting in a downward direction. So this is the vector which is acting in a downward direction. Its weight is always given by mg. Let us see how this all the vectors balances each other. The force of friction which is acting in an upward direction, it balances its weight of the vehicle mg which is acting in a downward direction. Also we know that normal reaction n is acting horizontally and towards the center, which is also equal to the centripetal force. Now this static friction which is exists between the wall and the tire has to prevent the downward slipping, and this magnitude is always equal to its mg as shown in this figure. From the vector equation we can make the equations. From a diagram it is observed that this normal reaction balances the centripetal force. Thus we can write down the n is equal to centripetal force, that is equal to m omega square r, that is equal to mv square upon r. In this we have to substitute the value of the omega. Also it is found that the frictional force vector balances its own weight vector, and therefore in magnitude we can write down the Fs is equal to mg. This frictional force or the static frictional force is always less than or equal to mu s n to perform the such kind of shunt, and therefore we can write down the Fs is equal to or less than mu s into n. So just substitute the value of the Fs and n from the equation 1 and 2. We get mg is less than or equal to mu s mv square upon r, where this is the n value which is equal to the centripetal force. and we get G value is less than or equal to mu s into v square upon r. Here the velocity must have the minimum value as the frictional force is less, and therefore v square must be greater than or equal to rg upon mu s. Rearrange this equation well and we get the v minimum is equal to square root of rg upon mu s. So this is the minimum speed of a vehicle to perform the shunt in a well-off deck or Mount Kakua.